Set up some focus notes. I do want to walk us through some key concepts today, and the 2 essential questions are listed there. So I'm going to give you a good 30, 45 seconds. And again, you can do this electronically. The template is down there, or actually, I think that's a capital. I think that should be a capital N. Pretty sure. So bit.ly. If you wanted to do it electronically, that would be what you would want to put, or via paper and pencil. So we're going to be talking about the difference between weight and mass. And we're talking about Newton's second law and free body diagrams. So, yeah. So what I'd love to see is if you could tell me in the chat when you're done, meaning you've kind of set up your focus notes, you've got your essential questions written down, and you're ready. Thank you, Will, for putting that. Will has put a link in to the digital focus notes template for those who want it. Thank you, Aiden. Muchas gracias, Lily. Lane and Flannery, thank you. Victor, Aiden, Elder, Henry, thank you, and Ellie as well. And Jake. Let's go about another 10 or 15 seconds. Looks like a good number of you are done or about done. Enough time for people to get another sip of their coffee or their tea or their energy drink. Who would drink an energy drink at this time? I bet someone's out there thinking, yeah. Okay, here we go. Want to start off with this idea. These are terms that are thrown around a lot in our society, and they have very specific definitions when we come to the physics world, and they sometimes get not used correctly. So I want to be really clear here. When we talk about someone's weight, right? I gained weight during the pandemic. That's certainly my case. In the physics world, weight is basically nothing other than the gravitational force of the Earth, the big massive planet that we live on, pulling down on you, okay? And we're going to spend more time talking about what that means like in a later unit. But for now, what you should know is, hopefully you've watched the videos from last week. If you haven't, make sure you do that, because I'm going to assume in these notes that you've seen that. So the weight of an object is the force due to gravity that object feels. And you can calculate that. You can calculate that by multiplying the mass of the object by the acceleration due to gravity. And for this to work, for this equation to work, the mass has to be in kilograms and the acceleration due to gravity has to be in meters per second squared. And if you do that, you get basically the SI unit. I don't write this down here, but the SI unit, I don't remember if this was in the things last week. I think it was, but the SI unit force is newtons. So 1 Newton is 1 kilogram meters per second squared. Or you could think of it as 1 Newton is the net force necessary to accelerate a mass, a 1 kilogram mass at 1 meter per second squared. So, but really what I want to do here is I just want to get this really basic idea down. If I have a 25 kilogram object and I ask you to calculate its weight, go ahead and do that really quickly. Let's assume G is 10 meters per second squared just to make the calculation easy. So again, you could either write that down on your paper or you could just kind of say it out loud. I'm going to give you a few more seconds. So if I was doing this, I would say M equals 25 kilograms, G is 10 meters per second squared. So just applying that formula from the top of the slide there, take the mass, multiply it by the acceleration due to gravity, and I get that the object's weight is 250 newtons. Okay, so next problem. I have 2 more sample problems for you, and here's what I want you to do. I want you to do both of them, but if your first name begins with the letter A through letter J, I want you to put your answer to question 2 in the chat when you've got an answer. If your first name begins with letter K through Z, I want you to put your answer to question 3 in the chat. So really, if your first name is K through Z, do number 3 first, and then do number 2. And A through J, do number 2 first, then number 3. Let's take 45 seconds here. Notice for these problems, I'd like you to assume the acceleration due to gravity is 9.80 meters per second squared. Okay, so let's look at this. An apple weighs approximately 1.35 newtons. What's its mass in kilograms? In this case, we're working backwards, right? So you have to solve for the mass. So the weight equals the mass times the acceleration due to gravity. Divide both sides by g. And you get the mass as the weight divided by the acceleration due to gravity. So when you do that, work it out, you get 0.137 or 138 kilograms. I may have rounded incorrectly there. So that's number 2. Number 3, you have a mid-sized sedan has a mass of 1,500 kilograms. I want to know what's the force due to gravity on the sedan. This is similar to problem 1. You just take the mass, multiply it by 9.8 meters per second squared, and you get your number. If you're being really particular with sig figs, you should round to 15,000 newtons, but 14,700 newtons, that's acceptable too. And part B, I just want to make sure you understand that force due to gravity and weight are synonymous, so they're the same thing. So the answer to part A and part B are identical to each other. Yes, you're correct, Victor. Couple things I just want to point out. These are mistakes, misconceptions, conceptual errors that high school students carry with them every year. And so I just want to be very explicit about them. So a lot of times I ask students determine the force due to gravity, or I ask them determine the weight, and they don't understand that the two are the same. Those are synonymous. If I ask you what's the force due to gravity on an object, that's the same thing as saying what is the object's weight. Okay. The other thing that I want to make sure we understand is weight is not the same thing as mass. Okay. Remember, mass is a measurement of the number of molecules, you could say, in an object, whereas the weight is a measure of the force, how strong of a force is exerted on it by another big object close by. The typical scenario that we could talk about, if I go to the moon, right? Well, let me just ask that question and you can answer in the chat. If Mr. Bob were to be transported to the moon, what would be the same or different about his weight, and what would be the same or different about his mass? So go ahead and just type an answer to that question. If Mr. Bob is transported to the moon, what is the same or different about the weight? What is the same or different about the mass? Yep, okay. I see Aiden, Jago, and Victor, Lena, Piper, Nathan, all correct. Very good. Okay, so let's talk about forces and free body diagrams. Let's consider a book that is falling through the air. In fact, you considered one earlier this year. So if I were to draw a free body diagram of the book, what I'm asking when I say that is I want you to draw, or I want a drawing that shows all the forces that the book feels. What we typically do is when we do that, we don't like draw these elaborate objects. We just reduce these objects to a point particle. And that just helps us simplify the drawings. It helps us not worry about something called rotational forces, because at this point in our conversation, I really don't want to talk about objects rotating. I just want to talk about them accelerating or not. Okay, so a typical free body diagram, you would show the book as a dot, and you would show an arrow, because forces are vectors. You would show an arrow in the direction that the for each force the object feels, you would show a force vector pointing in the direction that that force is causing the object to feel it. So in other words, if we say the surface of the earth is down, which we usually do, then this free body diagram would be just one arrow pointing straight down. And we always label our free body diagrams with the type of force that it is. So we would write, you could write W, or what you're going to see me often write is force due to gravity, F sub G. Okay, so, and as I just mentioned, the force due to gravity is drawn as a vector. And so that's what a free body diagram is. You're going to draw a lot of free body diagrams from now on. Now, when I ask you to solve problems involving forces and something called the net force, okay, what is the net force? So think of it this way. If I add up all the force vectors, remember we talked about adding vectors this year? If I add up all those force vectors that an object feels, then the net force is just like that resultant vector, okay? So, so when we talk about the net force on an object, it's really just taking all those vectors, adding them up, and seeing what is the resulting force. So here's some fancy looking equations, and I just want to make sure we understand what's what, okay? This Greek symbol is something you may have seen in math before, but if you haven't, that's okay. It's the Greek letter sigma, and it stands for sum of. So what all this is saying is if I add up the force vectors on an object, then I'm going to get the net force vector that that object feels. Similar to kinematics, to motion, what we can do now is we can just divide this up to make it simpler for us. We can talk about the forces acting on an object in the x direction, whatever direction we define as x, which is normally going to be horizontal, but not always. And I can also make a similar statement about if I look at all the force vectors acting just in the vertical direction, and I can talk about the sum of the forces in the vertical direction equaling the net force vector in the vertical direction. By the way, this is going to be in your updated equation sheet, which you'll see later on here. So here's an example. I have an object that has exactly two forces, all right? A 50 Newton force, you can see in the direction shown there, and a 30 Newton force shown in the direction here. And it's applied simultaneously to it. And so then the question is, what is the resultant force's magnitude? And you know, this is quite straightforward. What you do is we're just going to add them. Now, obviously I could vectorially add them. I could bring this up here and kind of go down here, right? And if I do that, and if I do it just right, the resultant force would show up, whoops, hold on, right here, okay? So if I wanted to, I could do it graphically, but we normally don't. In most cases, we don't, because, and this is why we kind of have these equations for the x and the y direction, because if we have them all in one direction, we can just define one direction as positive, say up, for example, and a second direction is negative, down, and then it's just a matter of adding or subtracting them algebraically. So in this case, the net force in the y direction is equal to the sum of the forces in the y direction, right? And so what I'm going to show you here is a little force table that you can do. Sum of the forces in the y direction, right? And you could just list them. In this case, I would list F2 minus F1. And then what's the net force in this case? The net force is just going to be their difference, right? And so in this case, we would just add them up and you'd get F net y equals negative 50 newtons plus 30 newtons. So net force in the y direction, in this case, is a negative 20 newtons. Or you could say 20 newtons down if you wanted to just keep the vector magnitude positive, but then just give it a direction. Either one would be acceptable. Okay. Awesome. Let me just take a look. We're doing good. Okay, so Newton's second law of motion. I'm going to talk about Newton's first law later because I just want to, the second law is more important for us for what we're doing today. So in Newton's second law of motion, what is this all about? Some of you may have been exposed to it before, but we're going to talk about it in a specific way that I like to. So Newton's second law basically says if I figure out the net force acting on an object, that is actually equal to the mass of the object times its acceleration. So you can see there, and I bet some of you walked in here knowing F equals ma. Well, I want you to think F net equals ma, okay? Because that's an important distinction. And here's a useful way to think about it. I would oftentimes ask you or suggest you think about it this way, that if I'm wondering what does the acceleration of an object depend on, okay? It depends on these two things. What's in this equation? Well, it depends on the net force the object feels. So the bigger the net force, the bigger the acceleration. Right? Because as this number goes up, this number is going to go up. What else does it depend on? Depends on obviously the thing in the denominator, which is the mass. And in this case, the bigger the mass, the smaller the acceleration. And again, we can make this equation, the one you see up there, specific to each direction. So I can say net force in the x direction equals mass times acceleration in the x direction. I can also say the net force in the y direction equals the mass times the acceleration in the y direction. And you will want to do that. In fact, you're going to do that here in a little bit. All right, we got to pause for a joke. Who's ready for one? How did the physics students make the hot dog shiver? They covered it with chili beans. I know a lot of you are laughing there inside. All right, you got a bonus today. You're going to get another joke. So let's go ahead and put all this knowledge to get to work with two sample problems. So what I'm going to do here is I'm just going to walk through two sample problems. And so what I want you to avoid is I don't want you to mindlessly copy, okay? Because you're actually going to get more sample problems to work in your groups and your breakout rooms here in a few minutes. So the most important is that you follow what's happening. Obviously, if you feel like it's best for you to take notes, please feel free to keep taking notes. But again, I would just say avoid just furiously copying down the problem statements word for word because you might not follow what I'm actually doing. All right, so here we go. The first one. Oh, this I would write down in your notes. So we've talked about DGUS, right? And while that's still important, when we get to free body diagrams and problems involving forces, there's really two important problem solving tips that I want you to always think about. The first is always, 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 even if I don't ask you to, always draw a free body diagram as your first step. And the second one is to always set up a forces table. And you'll see what I mean here in a moment. Okay, so here's sample problem number one. For this problem, we're going to assume that the acceleration due to gravity is 10 meters per second squared. So I have a 21 kilogram box that's sitting on the floor at rest, and I want to determine three things about it. The box's force due to gravity, the box's acceleration, and the normal force exerted on the box by the floor. Okay, three things I want to determine. And so what is the first most important problem solving tip? It's drawing a free body diagram, right? So let's go ahead and do that. I'm going to flip the slide here, but the problem statement is still going to be there. So There you see, same problem. So first thing we always do is we set up a free body diagram. So I'm going to reduce that box to a dot, right? A point particle. Now, as it's sitting there on the floor, it's near the surface of the earth. So we know one force that feels is the force due to gravity. Okay. Now, am I done? Is it kind of like the other situation? No. And if you're wondering why not, if you're kind of doubting that, the question would be like, if this was the only force, then that box would be moving, right? Because if you have a net force, then you have acceleration. In this case, this box is sitting still. So something else must be counteracting that gravitational force. And indeed, part C actually tells you, and if you didn't see the video last week and take notes on it, you want to do that because they talk about the normal force, a very important force that you're going to be intimately familiar with over the next few weeks. And so the normal force, the floor is pushing up on the box. And we call that whenever any sort of, what am I trying to say? I don't want to say horizontal because it's not always horizontal, but whenever any flat surface presses against another object, there's a normal force that's exerting. Okay, so there's my free body diagram. I've got those two forces. The next thing I would want to do is I would want to do a forces table. Okay, now you're going to eventually get to the point where we're going to have forces in both directions. So, right, you're going to want to figure out what are the forces in the y direction, what are the forces in the x direction. For this problem, we don't have any forces in the x direction, so we can kind of ignore that. So what are the forces in the y direction? And I also, again, I do have to set up a coordinate system. I'm going to do that here. Come on. There we go. All right, so the coordinate system is going to be that up is positive and down is negative. So what forces do I have in the y direction? Well, I have the normal force and I have negative FG, right? Because that points down. Okay. In this case, what is the net force? There's two things I could write down there. I could write this relationship, which is certainly true. I could also write, based on the problem statement, because it's at rest, okay, we know that this equals 0. The net force has to be 0 because it's not accelerating. Okay, so now let's just do letter A. Force due to gravity. Force due to gravity is mass times acceleration due to gravity. So that's going to be 21.0 kilograms times 10 meters per second squared, or 210 newtons. Okay, so there's part A. Part B, box's acceleration. I don't have to do any calculations on this. Remember, if it's at rest, what is acceleration? Acceleration would be 0, means A equals 0. Okay, now the normal force. How am I going to figure out the normal force? Well, that's where this equation down here is really key. Okay, since normal force minus the force due to gravity equals 0, if I add force due to gravity to both sides, I come up with this expression that the normal force is equal to the force due to gravity. So the normal force would be equal to 210 newtons. I bet some of you are saying, Mr. Bob, I knew that off the top of my head. Why do I have to go through all this? Well, the scenarios are going to get more complicated, as you can see here in a few minutes. So it's going to be important for you to keep track of all the forces and to keep track of the force equation, because you're going to have more than 2 terms in some cases. You might have 3 or 4 or 5 terms. Okay, so there we go. We've got problem 1 done. Woohoo! All right, we got one more problem, but first, a second joke. You got a bonus joke today. Yes, I know. Piper's jaw just dropped. What is an astronaut sandwich made of? Launch meat. Okay, I heard someone unmute but not laugh. I don't know what to think of that. Is that kind of like a deadpan, that wasn't funny? I don't know. All right. So last problem before you actually get into the breakout rooms. So in this sample problem, you can see that I am sitting on top of a box. Okay. And you can see there the 9.0 kilogram box is at rest. I'm on top of it. Okay. And so I want to know four things. I want to draw a free body diagram. I want to fill out the forces table. I want to write an equation for the sum of forces in the y direction. I want to determine the normal force. Okay. So here we go, free body diagram. Well, same as last problem, we have force due to gravity. And by the way, we're doing a free body diagram of the box. I just want to emphasize something. Sometimes students get confused because they say, well, wait a second, the box is pushing on the floor and the box is pushing up on Mr. Bob. Yes, but those are forces that I feel and the floor feels. A free body diagram is only about one and only one object. Okay, so we're going to ignore forces that the box is exerting on me, for example. We're just asking for what forces does the box feel. So it feels the force due to gravity from the earth. It also feels the normal force from the ground. And notice, I don't know what you want to call this. I'm going to call it an applied force. Okay, FAPP. Some of you might say, could I call it a normal force from Mr. Bob? Well, I'll just tell you my rear end isn't flat, so no. Okay, so applied force. All right, so we got three forces now. So in our forces table, again, we could ignore X direction. I just bring this up because eventually you're going to be seeing force diagrams, free body diagrams that have forces in the X direction and the Y direction, and at angles, by the way. But what do we have here? And again, if we say up is positive, down is negative, then we have normal force minus applied force minus force due to gravity. Okay, and all of that is equal to the net force. So, but we know the net force is what? We know the net force is 0 because the acceleration is 0, right? So we drew the free body diagram, we filled out the forces table. So now we have to write an equation for the sum of the forces in the y direction. So part C, sum of the forces in the y direction is going to equal the net force in the y direction, okay, which equals 0. So what we can do here is we can say the normal force minus the applied force minus the gravity force equals 0. Okay. I made this problem harder than I meant it to be, but you guys can handle it. Okay, so we're going to determine the normal force, right? The normal force, to do that, I'm going to add the applied force and I'm going to add the gravity force to both sides. So these cancel, and we get that the normal force is equal to the applied force plus the weight of the box. The weight of the box is what? The weight of the box is just going to be 9 kilograms times 10 meters per second squared, right? What is the applied force? Well, I'm just going to tell you the applied force in this case is equal to my weight, because notice my feet are dangling, so my whole body weight is supported by the box. So this was just going to be 85 kilograms times 10 meters per second squared. Okay, good clarification, Alec. So then the normal force is going to be 850 newtons plus another 90 newtons. And so that's a total of 940 newtons. Let me pause there. I know I threw a lot at you in those last 30 seconds. So again, if you have questions, feel free to put them in the chat. Just know you're going to get more practice with this in a second in your breakout rooms.